Okay, in this problem, this is about classifying substances. So when I need to classify as pure or mixture, remember pure means it is an element or a compound. Mixture means that it's at least two components, at least two substances. All right, so from that, and also then an element, remember I know that it has only one atoms of one element. I know that its name would be an element name, and its formula would be a single chemical symbol. For a compound, I know that it has atoms of two or more elements. I know that it will have parts of two element names. Again, in future chapters, we're going to properly learn how we actually name compounds. But for now, I know that it will have pieces of element names, or the two exceptions that are common names that I asked you to memorize is water and ammonia. And then the chemical formulas will have at least two symbols in the chemical formula. Now, when I'm looking at the mixtures, everything else will be a mixture. So I'm going to look at the name and determine, is it an element name? No, it is not on the element list. Is it a compound? In other words, does it have more than one? If it doesn't have one element from the list, it also doesn't have two. So because there are no element names, I'm going to assume that this is a mixture. We'll come back and decide how do I determine whether it's a homogeneous or heterogeneous one. Okay, sulfur dioxide. I see this is an element name, and this part is part of an element name. And I see two symbols. So I actually first can identify that this is a compound, which means that then it must be pure. So I'm just trying to figure out if it's pure or a mixture, but by determining if it's an element or a compound, that's kind of how I know it's pure. And so I'm kind of doing both at the same time. Whereas the mixtures, I'm going to have to go back and determine homogeneous or heterogeneous. So vanadium, this is an element name. So again, once again, I determine it's an element, which means it's pure. Salt water. Okay, water is a compound name, but this is something else, right? So I have two things. So this must be a mixture. All right, milk. There's no element names in this. So it must be a mixture. Xenon, this is an element name. Fluorine, so this is part of an element name. And I see two chemical symbols, so this is a compound. Again, once I've identified it's a compound, it's pure. Frequently for pure, I'm really identifying, is it an element, is it a compound? If so, it's pure, and I'm really doing the next step as well. And then if it's neither an element nor a compound, then it's a mixture. Copper, this is an element name, and there's only one of them, so this is an element, which means it's pure. Tantalum, this is an element name, so it's an element, so it's pure. And again, remember, there is a list of all 118 elements that you should refer to, because I know that this is an element name, you may not, but if you refer to the list, you look alphabetically in T's. If it's there, it's an element name. If it's not there, it's not an element name. So that becomes a really important thing. All right, now let's go back for these couple of mixtures and talk about homogeneous and non-homogeneous. Heterogeneous. So homogeneous, I cannot tell by the eye. Visually looks pure. In other words, it looks like it's one substance. Whereas heterogeneous, it's visibly visually at least two things. Okay, so let's look at what the description of granite would be. So again, I'm going to be referring to the imaginary image of granite in my head of like, I've looked at it before, I'm using my memory bank. If you don't know what granite is, you would probably need to go look up image of granite. But it is a gray, black, white, speckled rock. But the fact that it's speckled means that I can see that there's more than one component. So this would be non-uniform. So this would be a heterogeneous. I'm just going to write heterogeneous because I'm running out of room. All right, for this mixture, salt water, if I were to look at it, it looks like clear water. Maybe it's a little bit cloudy, but it looks like one substance. So I'm going to say that this one is uniform. This is a homogeneous. Milk, again, it's like a white liquid. It all appears to be one thing. So we would say that this is uniform or it's a homogeneous mixture. This is the easiest way to really attack these things, as I say, is it an element? Yes or no. If I've ruled out it's an element, then I ask, is it a compound? Yes or no. Once I've ruled it out, it's a compound. It must be a mixture. If it's a mixture, now I go looking for what would it look like visually to determine is it heterogeneous or homogeneous. For the third question says, which of these are elements? This is just compare to my list of elements, and either they're on it or they're not. In other words, it's really sort of important that you have that list memorized, especially the list of the 50 or so ones that I've asked you to memorize. But even the other ones, if I can recognize it's an element, I'm already up in the game. So this is an element. This is selenium. This is manganese, is Mn. Ammonia, no. This is a compound. It's one of the two compounds that I ask you to memorize. And then oxygen, yes, that is an element. Its symbol is O. All right, let's talk a little bit more about that physical change and the chemical change. Remember, one of the distinct things is that in a chemical change, we make a new substance. And in a physical change, it's the same substance. It may appear different, but it is the same substance, the same chemical formula. Remember, two things that are classically physical changes are, there are many, but two very distinct ones that you should be watching out for is change of state. So solid to liquid to gas, and mixing or separation. So if I'm mixing blue and red and I get something purple, although it's a drastic looking different, the purple is made up of red and blue. It's still the red and blue things, but because they're mixed together. So mixing and separating, so these two things can be tricky to look at because it appears very different. It appears like it might be a new substance, and yet upon closer look, it is the same substance. Okay, frying an egg. So frying, you might start thinking it's kind of like change of state, but not really. I mean, it is going from something that is liquid to something that is solid, but it actually undergoes a change. And one issue is that it's not reversible. In fact, it's very different properties. It has really changed over. So the frying, one of the things is that chemical changes tend to be non-reversibles. Whereas if I change the state and melt it, I can always freeze it back. If I mix it, I can always separate it back. So the physical changes are much more likely to be reversible. They are reversible. That doesn't always mean they're easy to reverse. So this one is going to be a chemical. Digesting carrots. Again, we know this happens in the stomach, and when you digest, it changes it into substances the body can use. So it's breaking it down. So it's no longer carrots. It's now been turned into other stuff. So this one would be chemical. Now, a MacBook falling out of a window, it may be in pieces, but still the same original substances. The MacBook, again, is a mixture. And so essentially, this is kind of like a separation. I'm now physically separating it into a whole bunch of little pieces. Ice cream melting, again, knowing our state changes, melting, boiling, freezing, condensing, this is a physical change. So we would say this one is a physical change, this one is a physical change. Dropping a fizzy tablet into a glass of water. Well, when this happens, again, this is now, I see bubbles, gas leaves the system, and I can't get that fizzy tablet back. If I were to evaporate it, it would not get me the fizzy tablet back. So this one is probably that would be, I would say this is how I would test it, is that if you evaporate the water, does the fizzy tablet powder, it wouldn't be in tablet form, remain? If that's a yes, then this would be a mixing, thus this would be a physical change. But if it's no, then that's a chemical. And I would say fizzy tablet isn't really clear. I don't know what you mean by the fizzy tablet. So this is a little bit vague. But if it is, if it's something like baking soda and it actually decomposes and breaks up and the gas leaves, then I can't get back the baking soda. It's no longer baking soda, it's converted. But if it's just dissolving, like a sugar tablet dissolving into water, then it might be. But I'm going to say that this is very likely to be chemical. Again, this is a little bit vague the way it's worded. But I'm talking you through the general way you could solve these problems. All right, C for chemical reaction, P for physical change. Continuing on the same thing. Burning leaves. So burning, again, remember, I start with leaves, and it gets converted to ash, and there's smoke released. Again, once that smoke is released, it's not coming back, and so it's not reversible. So this is a chemical. Cutting diamonds. This is really basically a separation, right? I'm separating it into smaller pieces. So this one would be physical. Crushing a pencil. Again, I'm separating it. It's still a pencil. It's the same substances, so that one's physical. The salivary amylase enzyme that breaks down food in the mouth. Again, I don't really know, but it's saying breaks down food. If it's broken it down and again, here I'm the words breakdown may sound like it's a separation, but the food is now no longer in its original format. I have made I've actually broken it up, broken bonds, and my body breaks it down into new substances. So this one would be chemical. Salt mixing in with water. Again, mixing, that's what I'm looking for, mixing and change of state. This one's physical. All right, looking at the scientific, remember, theory explains, hypothesis explains, and the law just states. And then this one is kind of preliminary. It's sort of not necessarily well supported, where this one is very well supported. Okay, water freezes at 32. There is no explanation here. This is just a statement. It's just saying this is what happens. So this one would be a law. The JN.1 variant is more contagious because So again, I'm seeing that explain because its glycoprotein mutations allow it to escape the immune system response. So because this is an explanation, so it's either going to be a hypothesis or theory. Now, a little bit tricky here is that now I need to know how well supported is this. If I'm not a researcher in this field, I don't know whether everybody commonly accepts that it's so well supported that yes, glycoprotein mutations are allowing it to escape the immune system, or whether this is just like a proposed explanation. So it might be hard to tell whether it's a hypothesis or theory if we don't have specific information. I would probably go with this one's more of a theory. But again, that would require knowledge of the field. But it is not a law. I can say it's a hypothesis or a theory. Matter is composed of atoms and thus mass is conserved in chemical changes and mass ratios of different compounds with the same elements will have small whole number ratios. So basically, mass is conserved in chemical change, so this is a law. And then mass ratios of different compounds with same elements will have small whole number ratios. This is a law. But this part is now, it's a little bit hidden because I'm not seeing the word because, but it's saying the reason that mass is conserved and that this has happened is because matter is composed of atoms. So this is now not a law. This is now an explanation. So this would be, now this is very well supported. So I would call this one a theory. And again, it's deceptive because you might think, oh yes, I'm relating that matter's composed, but it's really not relating properties. It is an exclamation. It is sort of doing this, it feels like a statement because you accept it as true, but it really is an explanation. Iron reacts with oxygen to produce rust. This is a statement. There is no explanation. It's not saying why it happens. It's just saying, here it is, it happens. So this one would be a law. This is magnesium reacts with oxygen more than nitrogen because, so I'm seeing this explanation, oxygen is more electronegative. Again, I don't know whether this is well supported or not, but we would probably say at this point, you may not be sure of how well supported this is. At the end of this course, you will. So I'm going to say theory. However, if you recognize that this is an explanation and it's a hypothesis or a theory, I'm quite happy. All right. An atom composed of which of these particles would have a mass of approximately 12 AMUs and be charge neutral? So word problems, I'm given that it is a mass of about 12 AMUs and that it is charge neutral. And I'm wanting to know basically the numbers of subatomic particles. So my plan for attack is really determining how does the mass relate to the number of subatomic particles? How does the charge relate? So I need to now use my knowledge of this information to sort of break this down and say, okay, the mass number, which is about equal to the mass, is equal to the number of neutrons plus the number of protons. So now that means I'm looking for, does number of neutrons plus number of protons equal 12? So when I'm looking at protons, this doesn't even say how many neutrons, but I'm looking at protons and neutrons, This doesn't tell me how many protons. Okay, so this one would be 3 plus 3 equals 6. This would be 6 plus 6 equals 12. So that meets the first part. Okay, the second part I'm looking at would be that charge neutral means that the number of protons must be equal to the number of electrons. So I have 6 protons and 6 electrons, and 6 equals 6. So that one's good there. But again, I can't confirm this, so I really shouldn't be picking this because without knowledge of how many neutrons I have, I can't say that the mass is 12. So this is no. And then 3 protons and 6, 3 does not equal 6. So this is a no. And I mean, we already knew it was no from that, but 6 protons and 6 electrons. So 6 equals 6. This one looks to be my correct answer, just to rule it off. Again, this would be 12 electrons. I don't know how many protons. Without a knowledge of protons, I can't say. And here I also can't say. So this one's a no. So that's how we could break it down. But then again, when I'm looking at these, I'm going back to how would I evaluate that and coming up with something. This is a very clear-cut criterion that now I can apply to these questions where I'm not guessing, I'm determining the answers. Which pair of ions has the same total number of electrons? Okay, so how do I determine the number of electrons? Well, the number of electrons would be, remember, I know that the number of protons minus, because they're a negative charge, the number of electrons equals the charge. So the number of electrons would be the, the number of, if I do some algebra, I would subtract, add electrons to both sides, subtract charge from both sides, minus the charge. So I will need to know the number of protons and the charge. Well, the charge is given. So this will be the first one, and then we'll do for the second one. So we will determine these for all of them. It's good practice. For the second one, we'll have number of protons and charge, and then we can write next to it. So I will first do the first one in each case. Note that to get the number of protons is the atomic number of that element. So let's look up. So sodium is 11, magnesium is 12, fluorine is 9, chlorine is 17, oxygen is 8, gallium is 31, and iron is 26. Okay. So this would be, for the first one, sodium is 11, fluorine is 9, oxygen is 8, gallium is 31, and the charge is +1, -1, -1, +3. So if I can subtract the protons, the charge, the protons minus the charge, I get 10. And this one would be 9. Remember, 9 minus a -1 is really 10. 8 minus a -1 is 9. 31 minus 3 is 28. Let's do that now for the other one in the series. Okay, and again, you might be able to guess and test one and get there faster, but we're practicing along the way. So we're getting our skills basically. So magnesium is 12. Chlorine is 17, oxygen is still 8, iron is 26, and then the charge, this one is 2, this one is -1, -2, +3. And so when I subtract them, the protons minus the charge, so this one's 10. Okay, so note that right away we got the first one, but 17 minus 1 is 16. Oh wait, minus -1, sorry. 18, watch out. 8 minus negative 2, this one's 10. 26 minus 3 is 23. So this is the only one where they match. But this is good practice in determining the number of electrons. So by doing this while we're doing our practice, if you were on a test and time were concerned, you might want to try to get there more quickly and look for some patterns. It is unlikely that if they have the same charge and they're not the same element, then they're not going to have the same number of electrons, because I'm looking, I need them to match up to subtract to be equal. So I might be able to look for some patterns and make a better guess and then test it using this rule. But when we're doing practice, we really, now I've practiced 8 times, I have a better idea of how to do this. How many protons, neutrons, and electrons are in calcium 42? So I know that the mass number equals 42, and I know the element equals calcium. Also, let's go through our facts. Remember, mass number equals protons plus neutrons. Charge equals the number of protons minus the number of electrons, because electrons are negatively charged, so I subtract the number of those. And I know that the atomic number is the number of protons. So those are my little facts that are going to help me along with this. So if I know the mass is 42, so first I want to know that the atomic number of calcium is, I think it's 20. Yes, it's 20. So I know that the mass is protons plus neutrons, and of them, I know 20 of them are due to the protons. So 42 minus 20 equals 22. So that's going to be equal to what my neutrons are. And then for there is no charge. Should have written that down. So protons must equal the number of electrons. Okay, so my protons is 20, my neutrons is 22, and my electrons is the same as the protons, is 20. How many protons, neutrons, electrons are in 37? Chlorine minus. Again, my mass number is 37. Chlorine's atomic number is 17. And that's equal to my protons, so my protons equals 17. And 37 equals 17 plus n, so I subtract 17 from both sides. My number of neutrons are going to be 20. And then my charge is -1. So you can either use math and say that the protons minus the electrons equals -1, and I know the protons is 17 minus E equals -1, and then I'm going to kind of do some math and figure it out. Or I could say this means that there are one more electron than proton, because that's how it has a negative charge. So I'm just going to take the number of protons, 17, and I'm going to add one more, and I get 18. Either way, I'd get that there are 18 electrons. So in this case, I'd have to find that -1E equals -1 minus 17 equals -18, and then so E equals 18. So the math is actually harder doing it by algebra than kind of talking yourself through it, but both methods will work. Write the isotope symbol for an atom with 67 protons and 71 neutrons. Again, my isotope symbol, I need to know the mass number, right? It is mass number, atomic number, and symbol. And then the charge. So to do that, I'm looking for the mass number, which is equal to the number of neutrons plus protons. I need to know the atomic number. I need to know, which is equal to the protons. I need to know the charge, which is equal to the protons minus the electrons. And I need to know the symbol, which I can get once I know the atomic number. Okay, so I know I have 67 protons. So this is 67. And 71 neutrons. So this is 71 plus 67. And it says it's an atom, So, because atom means neutral. So I don't really need to do any calculations. And then the symbol, I'm going to look up 67. And it's down at the bottom. So 67 is holmium. So 67 holmium, and I have to add that up. 1 plus 7 is 8, 13, so 138. And there is no charge because it's neutral. Write the isotope symbol for an atom with 28 electrons. Mass number equals protons plus neutrons. Atomic number is the number of protons. The charge equals the protons minus the electrons. But it says atom, so it's equal to 0. And the symbol I'm going to get from the number of protons. So it doesn't tell me. It tells me I have 28 electrons. But if the charge is 0, the number of protons equals the number of electrons. So protons is equal, which is equal to 28. So that means this is equal to 28. And then, if I know that, I can say this is 28 plus 30 neutrons is given. So that's 58. And then for 28, I go look up 28. And it is nickel. So I get nickel, 28, 58 for my answer. Which part of the atom has more mass, the nucleus or the outer region? Well, let me think about my facts. I know that the protons and neutrons are in the nucleus. And I know the electrons are in the outer region. And I know for the mass, the protons are 1 AMUs, the neutrons are 1 AMUs, and I know that the electrons are effectively 0 AMUs. So all of the mass, this is where most of the mass is. So it's in the nucleus. How many electrons are in 118? Tin 118 with a +4 charge. It's a little tricky here because I have a charge to worry about. I know that my charge is equal to the protons minus the electrons, right? And so, and I know that the number of protons, if I look up the atomic number of tin, it's 50. So I know I have 50 protons. Now, I could do this two ways. I could say 4 plus equals 50 minus E and then work out the answers. Or I could say this means that it lost 4 electrons to get 4 plus. So if I started with 50 minus 4, I would get 46. Or I could just kind of figure this out from, okay, that 50 minus 46 equals 4. Either way, so I get that there are 46 electrons. Without looking at the periodic table, which of these isotope symbols are invalid? I'm just looking for general predictions, things that I know. I know that the top number is the mass number, which is the number of protons plus neutrons, and I know that the bottom number is the atomic number, which is the number of protons. So without looking at a periodic table, I couldn't do things like say, is this the right chemical symbol for that atomic number? But I know that this has to be an integer. It must be a whole number. And I also know that the mass number must be bigger than the atomic number because it includes the atomic number, right? This is part of the mass number, so the mass number must be bigger. So from that, I see this is bigger and it's a whole number. So as far as I can't obviously tell if there's an issue with it, but this is not a whole number. And this is not bigger. So this is not a whole. That's not proper. This is bigger and it's a whole number. So as far as I can tell, it looks good too. So I would say for sure, these are problematic. So be careful. Like sometimes I can look at it and be careful when you're writing your answers. You know that this has to be whole numbers and you know that the bigger number must be on top. So don't get that confused. Write the isotope symbol for a +2 cation with 36 electrons and 48 neutrons. Okay, so again, isotope symbol, I know I need the mass number up here, which is protons plus neutrons. I know I need the atomic number down here, which is the number of protons. I need the symbol, and then I need the charge. All right, so from that, I know it tells me I have 30, the electrons is 36, and I know the neutrons is 48. I don't know the protons, but I know that +2 means it lost 2 electrons. So 48 was how many, like it lost 2 to get to 48, which means originally it was 50. Or if you're like that, talking it through is tricky, I could say that the charge is equal to the protons minus the electrons. I know +2 equals P minus 36. So P has to be, I did wrong, I did 38. How did I get +2? Lots to, I think I was looking at the 48, sorry, this should be 36. So 36 means it originally should have been 38. So maybe I did better doing this way. All right, so if the protons are 38, then that's my atomic number. So that's 38. And then my mass number is going to be 38 plus 48. So that's 70 and 1686. And I'm going to, and my charge is 2 plus. Remember, we typically write it with this number, then the sign. When we're writing charge, even though we can say that the charge is +2, when we write it in the symbol, we write the number first. If you write the +2, there's no problem with it. It's okay. So 38's symbol for 38 is strontium. And there you go.